Okay, good morning, students. Today is Monday, November 29th. Basically, the year is almost over. Today, I'm going to do a correction because I made a mistake when I gave you the instructions to model in the center line. The symmetry conditions are not correct in general. So I have to make a correction about that. Then I'm going to go on with the material. We're going to deduce what we call a compatibility equation. That's typical when we solve what we call plane stress problems. And then in the last part of the class, Engineer Isaac will be sharing with you some observations that I made about your reports. Okay, with your reports, I found that there are some common ways to improve them, since we still have at least 2 more projects, one small about plane stress and the final report. So I think it's a good idea that you receive a feedback how to improve them. Okay, so that's the things that we're going to cover this morning. So let's start. So I'm going to share the screen with this. Okay, so can you see my screen, Isaac? Isaac, can you see my screen?
Yes, doctor.
Okay, thank you. So, if I put a pen here, thickness is 1 point. Okay, so in general, okay, when we have symmetry, okay, so for example, we have a deck frame, okay, like that. Here we have the side, something like this. And here we have the center line. Okay, so this is center line. Okay, this, of course, is let's suppose that we include here a joint. Okay, so if we have symmetry, for example, I have an application of the load here and a symmetrical load down here. Let me change color. This is going to deform. It can move downwards, right? But it cannot rotate in the transversal direction, and it can also cannot rotate. So this is the only displacement that this point can take. Okay, so in general, okay, if we call this, let's include here a reference system. Let's suppose this is Y and this is Z. Okay, so this point here cannot move in the Y direction. It cannot rotate in the X direction. This is going to be X. So the restrictions would be no displacement in Y direction and no rotation in the X direction. These are the correct restrictions. In our project, what I did was I simplify your calculations, and I ask you to consider this point as a clamped end. I think this is correct, okay? In some cases, you have a vertical element here, and in that case, the displacement in the vertical direction, in the Z direction, is very small, okay? But I ask you to consider this joint as a clamped point, and this is not completely correct, okay? As a simplification, okay, in the first project, we considered this point to be clamped, but it is better to consider as guided. Okay, see, these two conditions, okay, remind us that this point can, if this point can move in the vertical direction, but it cannot move in the y direction, or it cannot rotate. Basically, this is a guided end. Okay, so this is what we call a guided. Maybe you remember this from mechanical engineering, from solid mechanics. Okay, so this is what we did in the project, okay? This is oversimplification. So I think it's more precise if we take these conditions as restrictions, okay? In case you have a vertical element, okay, if we consider as clamped, it's going to be very good. But in general, this is the two conditions that we should imply in this point, not clamped, but guided. Okay, so you will allow to move this point in the vertical, in the Z direction. Okay, is there any questions about this, people? Is there any questions about this?
Dr. Horner, Mr. Jimenez.
Go on.
The condition is just for, we had symmetry, just for the point symmetry, right?
Yes, yes. That's only, that, because I'm showing you that it's not only, when I say symmetry conditions, I mean geometry and load. Okay, for example, let's suppose I have the load only on one side. In that case, the rotation and probably the translation in the x direction will not be zero. So this is exactly as I said before. You have both conditions of symmetry, geometry and the load. In that case, yes, this point cannot move in the y direction and cannot rotate in the x direction. Mr. Jimenez?
Yes, doctor. For the last line in the, read this word.
Yeah, this is what we did in the project. We considered that this point would be clamped, and that's not completely correct, okay? This point should be able to move in the vertical direction, but I just simplified in this way, because in some cases, students get confused. But after seeing the results, okay, in some groups, try to discuss the deflection of the beam, of the deck beam, okay? And they mentioned that they had a very large bending moment around this area. And that's because we considered that as clamped. And that's not realistic. That's why I'm doing this correction. Okay?
Thank you.
Okay, no problem, no problem. Okay, so that's the first point. Let's go now to the second point of this class. So I'm going to share my other screen here. So this is the contents of this chapter. So far, we have covered points 1 and 2. So this is already, done, and these two. Okay, so we used minimum potential energy to solve or to deduce the bar stiffness matrix. Then we use minimum potential energy to obtain equivalent forces in the case of beam problems. Now we will go on with the plane stress problems, okay? Okay, so plane stress problems. Before we start with that, let's make a difference here. Okay, remember, probably you remember that in previous chapter, we had a bar element and also we have a beam element, okay? And both were very long elements, right? Long elements. But what was the difference? Somebody remembers the difference between a bar and a beam? Mr. Galarza, do you remember the difference between a bar and a beam?
Yes, doctor. In the case of the beam, we can consider the inertia. And in the case of the bar, we don't consider the inertia because the transversal area is less compared with the beam.
More than that, you're right.
Okay, the loads.
The load, yes,
exactly. We
exactly.
apply lateral loads and in the bars axial.
Exactly. So in this case, we apply, this is the load that we apply. In this case, this is the load that we apply. Okay, something similar to that, we're going to have here. In ship structure, we consider a plate, okay? And a plate, we consider that it's an element, which is, we have one of the dimensions, the thickness, is very small when you compare it to the other two dimensions, okay? So this is what we studied in ship structure. And in this chapter, in ship structure, we consider that the plate was like this. So this problem here that we studied previously is what we call plate bending, okay? So this is plate bending, okay? In this subchapter, we are going to study a plate, okay? So we're going to consider that we have similarly, in both cases, we have that the thickness is much smaller than the A or the B dimensions, okay? So this is the thickness. But now, similarly to the bar and beam difference, in this case, we apply the load only in the plane. If I can find my here it is. My dot, what is my dot? Here is my dot. So I have, this is the load. So in this chapter, in this subchapter, we're going to have the load applied in the plane of the plate. Okay, so in this case, for example, let's suppose that we call this, let's call this X, and let's call this Y. So the loads is going to be applied in the XY plane, while when we talk about plate bending, we apply it in the lateral direction. So that's in the perpendicular direction with respect to the XY plane. So let's put this is X and this is Y. Okay, so this is what we are going to be working with in this subchapter. And this is what we call plane stress. Okay, so in the general case, we are going to say, okay, if we have both lateral and in-plane loads, what we do basically is we superimpose effects. Similarly with what we did in the case of the bar and the beam. Okay, so let's go on. We're going to deduce this equation that we call a compatibility equation. And the reason to do that is that in general, when we talk about, when we work about plane stress problems, we usually introduce the definition of a function, what we call a Airy stress function. And once we do that, automatically the equilibrium equations are satisfied, okay? And since those are satisfied, we need another equation to solve for these problems. And that equation is what we call the compatibility equation. So that's what we're going to deduce, okay? Now, in the meantime, okay, we're going to review some basic concepts about plates, okay? So basically that's more important than the compatibility equation, okay? So when we work with plane stress problems, we consider three elements of the stress tensor. Okay, so we're going to be working with sigma x, sigma y, and tau xy. Okay, so in general, this is going to be our reference system. We're going to have a plate like this. Remember that the thickness is very small in general. This is going to be x, this is going to be y. Okay, and this, in this case, C is going to be downwards. Okay. As we said before, the load is going to be applied in the XY plane. So we're going to have forces like this. This is going to be our force in the X direction, force in the Y direction. Or we could have a force in the XY direction, like a shear, but always in the plane. Okay? So forces, in this case, it's going to be Fx, Fy, or Fxy will be acting in the XY plane. Okay, we have nothing that causes bending, only in the plane. Okay, so in this case, one point here, okay, this point, let me change color, this point here, after we apply this load, can move in the X and also in the Y direction. So this is what we will call U, and this we will call V. Okay. As a result, we will have that point at XY will move in the X and Y directions. So we're going to have that this point will move in the X direction an amount U, and in the Y direction a different amount V. So we're going to need to find two amounts or two displacements, okay, U and V. And the problem is that we are saying that we are interested in these three components of the stress. So you see, I have two here, and these two will define three stresses. So this difference in number forces us to deduce a relation so we don't have strange results. Let's call it in this way. Okay, that's why we need a compatibility equation. Okay, so let's continue with our review of some basic assumption, or no, basic relations. Okay, so let's remember the relations between strains and displacements. Okay, so epsilon x, remember, is equal to du dx. Please notice that in this case, the derivatives are partial because u depends on x and also on y. Epsilon y is dv dy. And in this case, we also need gamma xy. Mr. Zamora, do you remember the definition of gamma xy? Mr. Zamora, are you there? Mr. Zamora, are you there? Do you remember the definition of gamma xy? Mr. Zamora, no? Mr. Diaz, do you remember the definition of gamma xy? Mr. Carrillo, do you remember the definition of gamma xy? Mr.
Yes.
Please.
Multiply J.
Pardon me? Would you repeat that?
The U over the J.
Du, dy, okay. Go on. Plus
dV over dx.
Exactly. Thank you.
Okay.
You see that we have the definition of three parameters, epsilon x, epsilon y, and gamma, as function of only two parameters, u and v. And that's why we need a compatibility. Okay. So we will be working in the elastic range so we can relate these three parameters we can relate them to the stress sigma x, sigma y, and tau xy. Remember that we separate normal from shear. This is 0, this is 0. So these are related to that, and this is related to that. So here, when we have 1 over E, here we have minus nu over E. This is symmetric, and this is 1 over E. Here, it's 1 over G. Ms. Matias, do you remember the relationship between G and E? Ms. Matias, do you remember the relationship between G and E? Ms. Matias, no? Mr. Ramon, do you remember the relationship between G and E? Between G and E?
No, Doctor.
Here, no? Mr. Ordóñez, do you remember the relationship between G and E?
duration.
Yeah, but how much? Do you remember what do we have in the denominator?
1 minus
1
8.
plus, no. That's the relationship. That's something that we should keep in our memory, okay? G, that's the shear modulus, is equal to the Young modulus divided by 2, 1 plus nu, and nu is Poisson's ratio. Okay, now, from here, we can go and express the stresses as function of the strains, okay? And that's something that we did in shear structure. So in shear structure, we deduce this relationship. So if you need to remind, go back to your class notes. And here we have a common factor, which is 1 minus nu squared. And again, here we have, it's a good idea to separate normal and shear strains. Here. And here we have 1, this is nu, this is symmetric, this is 1, no, no, and here we have 1 minus nu divided by 2. Okay, oh, here is 2, sorry. There. So this is the relationship between strains and stresses. Okay, we assume that we're going to be working in the elastic range. Now, let's go to equilibrium. Okay, let's suppose that we have a plate here. Okay, so this is the X direction, this is the Y direction, okay? And we know that we have forces like this. Say, we're going to take an arbitrary element here, okay? And that arbitrary element here is going to be defined between these two lines, okay? So up to here, this is X, and this distance is dx. And similarly, in the Y direction, this cut is at position Y, and it comes up to this. So we take this is an arbitrary element, and we see from above, and this is what we have. Okay, so let's suppose this H is at position X, and the distance between this and these sides are dx. Similarly, this distance is dy. Okay, so remember that internal forces on this side are different than the internal forces in this side. Okay, so if this is X direction, this is sigma X. So on the other side, we're going to have sigma X, but we're going to have a little change. Okay, from here to here, this is going to be the derivative times, let me erase this because we need more space. Here. Okay, times dx. So the distance from here to here is dy. So in general, okay, if we take this stress multiplied by dy and the thickness, that will give us the force because of this stress. Similarly in the other direction. Okay, now we're going to do this in the only in the X direction. and we will assume that the similar expression will be deduced in the y direction. So on this side, okay, this is the negative side. So this is going to be tau. It's going to be y because it's perpendicular to the y-axis, x because it points in the x direction. And then on the other side, we're going to have this similarly, but we have to include a change because it's a different cut. There's going to be the variation, but in this, it's going to be the y direction times the y. So equilibrium in x direction. So we have summation of forces in the x direction has to be equal to 0. So we have this force and this force, they both point in the positive x direction. Now this one here, so this is sigma x plus the change of that in the x direction. So this is stress. So we have to multiply by the area, this area here. So the length is dy, and we have in the vertical direction, perpendicular to the plane, we have the thickness. So this is equal to, this area is equal to t times dy. We have also this other force here, which is t yx plus the rate of change, but in the y direction. And we need to multiply by the area. It's going to be dx times the thickness. Now, this and that is going to be negative, are going to be negative sigma x times t dy and minus t yx, t dx, and all of that has to be 0. So this cancels that. This cancels that. And then we see that we have dx dyt, dx dyt, so that's common. So we call it this like that. And the result is going to be that this term plus this term has to be equal to 0. So we can say that this plus equal to 0. Okay? From equilibrium in y direction, so that's summation of forces in the y direction equal to 0, we're going to get something similar to this. So it's going to be the derivative of sigma y, but in the y direction, plus now we have to consider the shear, but in the y direction, and that's to equal to 0. And finally, from equilibrium of moment. And that's something that we did in solid mechanics. When we do that, we get that tau xy is equal to tau yx. Okay, so that's summation of moments in the z direction has to be equal to 0. So we have these three relationships, okay, to solve. And what we do, and when we work with this type of problems, is to define a new function, okay? Let's call it. And this new function is what we call a stress function. We solve these problems defining what we call an Airy stress function, okay? Some people call it Airy. Okay, there are some other versions of this name, but this is, I guess this is one of the most common way to call it, Airy stress function. So we define it like this. So sigma x is related to this Airy stress function as the second derivative of the Airy stress function with respect to y. Okay? Sigma y is defined as the second derivative of phi with respect to x. And tau, xy, is going to be equal to the negative of the mixed derivative of the AD stress function. Okay, so notice that I'm going to change color here. Notice, let's suppose that we have, let's recall from the previous page, the first equation, this one here. So let's, we have the second derivative, this first derivative of sigma x with respect to x plus this first derivative like that. So if I put this, okay, definition of sigma x, I'm going to get, so I'm going to get phi yy, okay, and now it's differentiated with respect to x. And now here we have tau yx, so it's equal to minus phi xy. And now it's differentiated with respect to y, so we get something like this. And you see here that I have two derivatives with respect to y and one with respect to x. Similar here, but this is negative, so this is identically equal to 0. So if we take this, the definition of for the Airy stress function like this, identically we satisfy equilibrium. And you can check that this is equal for the other relationship, for summation of forces in y direction. Okay, so this is typical. Okay, so when we take these definitions, in general, we can consider that the equilibrium equations are satisfied. We can do similarly for equilibrium of forces in the y direction. So we can say that equilibrium is satisfied. So if equilibrium is satisfied with this, we need another equation to solve. So we need another equation for this type of problems. And these are the compatibility equations, which are going to be deduced now. Okay, it's quite simple. And it goes like this. Let's suppose we have two functions which are continuous and differentiable. So we have u and v. Okay, so we could have, for example, the derivative of u and the derivative of y And we can differentiate this one here two times with respect to y. We can take this one here and differentiate it twice with respect to x. Okay, so here I have the derivative of u twice with respect to y and one with respect to x. Similarly for the y. Okay, so we can express this as since we have assumed that these two functions are continuous and differentiable, we can change the order of differentiation. And we can say that is equal to du dy plus dv dx. And we can differentiate that with respect to x and y previously. Okay, so this is an identity. If u and v are continuous indifferentiable. Now, that's an identity, right? Because all what we need to do is change the order of differentiation, and we get this term converted into this one here. Similarly for the other one. But now you can see that this is equal to epsilon x, this is equal to epsilon y, and this is equal to gamma xy. But now epsilon x, let me go back, epsilon x here is equal to 1 over e times sigma x minus nu over e sigma y. And sigma x and sigma y were defined using Airy's stress function, like this. So we can say that this is equal to sigma x over e minus nu sigma y over e. Right? That's Hooke's law here. And now let's replace the definition of Airy's stress function. So we can say that instead of sigma x, we're going to write, this is the second derivative over e. This is minus nu over e. It's going to be the second derivative with respect to x. This one here is going to be pxx over e minus nu pyy over e. And this one here, remember that these two terms are differentiated twice with respect to y, in this one here twice with respect to x. And this one here is going to be pxy, is going to be tau xy with respect to g. And g is going to be equal to e to 1 plus nu tau xy. So this term here is going to be minus 2, 1 plus nu over e phi xy. Okay, so this is the differentiated twice with respect to x and y. This is differentiated twice with respect to x. And this is differentiated twice with respect to y. Like that. And we see that I have, I'm sorry, this plus has to become here. Let me stick here. This is not this. There. This parenthesis goes here. So I have, see, this this is the mixed derivative of phi with negative sign. This is also a mixed derivative, so we have 2. And here we have the mixed derivative multiplied by 2 and by nu. So this will cancel this and that. So at the end, we're going to have this term here, this and that. And you see that the 3 have e, so I can cancel the e in the denominator like that. Okay, so as a result, we're going to have so the fourth derivative in x plus twice and plus the fourth derivative in y. That's what we call the compatibility equation. Sometimes we write it like this in a compact way. Okay, so this is the equation that we have to solve when we work with plane stress problems. And we had make a quick review of the relationships that we're going to use for this subchapter. Okay. Is there any questions about these people? Any questions? Any question? I hope you see that when we review these things, we are working with or reviewing basic relationships. And in some cases, you see that some of you do not remember some of the terminology. And that's something that we should worry about, okay? Because this is something that we need in order to handle our relationships. So please, if you don't remember these equations, try to practice at home, okay? Because it's something that we need, okay? For example, the relationship between G and E. Okay, yeah, you can go back and look it up in your notes, but it's better, it's much easier if we just remember from previous classes, okay? I don't know if there is no more question, then that will be all with me, and you will go on when we return with, you will be working with Engineer Isaac about the general recommendations that I gave it to you about preparing the reports, okay? If there are no questions, then I'll see you Thursday. And you will be, in 5 minutes, you will be going back to this room and work with Engineer Isaac. Okay, Engineer Isaac, can you hear me?
Yes, doctor.
Okay, so you're in charge now. Okay, I'm going to make you the host. Okay, so you're host now.